let's look at how to read our zero isoclines for the Lotka Voltera competition graphs. Our zero isoclines are basically, we're looking at a population isocline when the other species is not being represented on the same graph, but it's still experiencing competition. And so our species 1 is represented by this x-axis. We write our K1 over here, our carrying capacity. Our population line goes from the K1 over here to this point, which is representative of the competition that our species 1 faces. What we need to know is if we have random points on the graph, just like these gray ones, or you can draw anything you want. If we have these points, and we have our isocline, over time we need to know how these points are going to move. These points are just a representation of population size, and so if our population's over here, right, way above our isocline, way above our carrying capacity, it means that over time our population is going to need to reduce. A reduction means going towards our line or going left. For species 1. So for any random point that is above our line, we're going to go left to which represents a reduction in our population. And if you're below the carrying capacity or below this isocline, we're going to go right to represent an increase in our population. And so when we're looking at species 2, which is represented on the y-axis over here, we go from carrying capacity to the effect of competition, and we have points on the graph like that. We have our population line or isocline over here, and if we're above our carrying capacity, we're going to move down or towards our isocline. Going down to reduce our population, that means towards our isocline. If we're below the line, then we're going to go up, representing increasing our population to go towards our isocline or our carrying capacity. And that's basically what we need to know. But we're going to look at what this looks like when both the populations are represented on the same graph. So in this unstable equilibrium, when we have both population 1, which is ground finch, and population 2, which is tree finch, in the same graph. If I am over here, that's my point. Let me use a different color. I'm over here, and let's look at population 1, our ground finch. We're way above the carrying capacity. We're going to move to the right. Let's look at population number 2, our tree finch. We're way above our carrying capacity, which is this line, so we're going to move down. The gray lines are actually, these gray lines are the vector sums of these two movements. And why this graph is an unstable equilibrium is because our final arrows, our vector arrows, are pointing in different directions. They're not going towards one certain outcome. And so we're going to need more information or more observations over time to see which species is winning. When we go to stable equilibrium, our vectors are actually mostly pointing towards the middle, or the point where our isoclines interact, which means that both the species are coexisting and no one is outcompeting the other.